Hi everyone, this is BB Sangmay, and today I'm going to discuss about the problem of design of turnbuckle. Okay, so this is the second problem. Do subscribe for the upcoming videos of machine design. So here the pull in the tie rod of an iron roof truss is 60 kilonewton. This is the applied force P. Design a suitable adjustable screw joint, means we have to design a turnbuckle. The permissible stresses are 75 MPa in tension, so this is the permissible tensile stress. 45 MPa in shear, this is the permissible shear stress, and 90 MPa in crushing, this is the permissible crushing stress. And again we have to they have in the problem the provided data regarding the selection of bolt or threads or the pitch of the bolt. We are going to refer this data which is already provided in the numerical. So let us see what we have in the given. So we in the problem we have the load axial pull type of a load of 60,000 Newton. Permissible stress in tension 75 Newton per mm square, permissible stress in shear 45 Newton per mm square, and permissible stress in crushing it is 90 Newton per mm square. So here you can see the figure of turnbuckle. Okay, so here as I have already discussed it during the design of turnbuckle, first we are going to calculate the core diameter of threads. So as here you can see that after the application of force there is a possibility of failure of threads at the minimum, that is the core diameter. Okay, so here while designing the threaded portion we are going to select the design load which is 30% more than the nominal or the given load. Then the given load is 60,000 Newton, and let us calculate the design load PD is equals to, which is 1.3 times P, so it is 78,000 Newton. So while designing the threaded portion we have to select the design we have to consider the design load. Okay, and during the remaining design procedure of the other than the threaded portion we have to consider the nominal load, that is load of 60,000 Newton. Okay, so let us calculate the core diameter, that is the diameter root diameter of threads. Okay, so as we know that after the application of force there is a possibility of failure of rod in tension, so sigma T will be equals to PD divided by the cross sectional area of the core diameter of thread is pi by 4 DC square. So I am going to rewrite this equation in terms of DC. Okay, so it will be DC is equals to root of 4 PD divided by sigma pi into sigma T. Okay, so here PD is the design load, because we have considered the design load because we are here right now we are dealing with the threaded portion. Sigma T is the permissible stress and tension, which is 75 Newton per mm square, already provided in the numerical. So by using this formula we can calculate DC. So as per the calculation I found that DC is 36.389 mm. So in this table they have provided the core diameter for the bolt. These are the various core diameters. Okay, and also according to the calculated core diameter we have to select the standard bolt with a designation, maybe it may be for M39, it may be M42. So let us see which standard dimension or which standard bolt is available in the market for this diameter. The calculated diameter is 36.389. so let us check whether this is available or not. Okay, so exact 36.389 is not available. We have 33.402. we have two values at here. Okay, one is the less than 36.389. so this is we have to select from the core diameter. This is the column of core diameter. Okay, so we have the one digit less than 36.389, which is 34.093, and we have one more greater value of core diameter, 36.416. okay, so we are going to prefer the larger one to keep the design safe. Okay, so let us select this 36.416 from the table. Okay, so from the table I am going to select the value of 36.416 for the core diameter, and for the same core diameter the measure diameter or nominal diameter will be 42 mm. Here you can see that for the same core diameter which we have selected for the 36.416 the measure value will be 42 mm. So here I have selected the measure diameter 42 mm and core diameter of 36.416. 416. So here we have calculated the dimensions of threaded portion of the bolt, okay, or the rod. The core diameter is 36.416 from the table, and the nominal or measure diameter is 42 mm. So it means that we have to select the standard size M42 bolt for the coupler nut for the applied load of 78,000 for the design load of 78,000 Newton. Okay, so next is the length of coupler nut. Okay, so here we can see that this is the coupler nut, okay, in which the threaded part is there, and this is the length of coupler nut. As I have already explained during the design procedure, after the application of load P, there is a possibility of failure of threads of coupler nut along this direction. Okay, so after the application of force, there is a possibility of failure of threads in direct shear. So we can calculate the length by using the formula of direct shear failure of nuts. So it will be tau is equals to P by A. Here again we are dealing with the threaded portion, so I am going to consider the design load PD. Okay, so tau will be equals to PD by A. Then we have let us calculate the area under shear. So obviously after the application of load, here you can see that the DC is the minimum diameter, okay, and there is a possibility of failure of threads at this point. Okay, at this point the threads are going to fail. It means that when you will apply a force of magnitude P in this direction, okay, so possibility of failure of threaded portion, it will fail in shear along this plane. Okay, so we are going to calculate the area under shear. Okay, so area of under shear will be equals to A is equals to we need to consider the cross sectional area of one thread. Okay, so it is not a cross sectional area, we need to consider the circumferential area. So we need to find out this area, which is pi DC into L. L means number of threads. If L is actually it is not number of threads, it is the length of coupler nut. If the length of coupler nut will be more, number of threads are going to increase. Okay, so here the area under shear will be pi DC into L. Okay, so to keep the coupler nut in strong in shear, or to reduce the induced shear stress, we are supposed to increase this area. So we can increase the area by increasing the value of DC, but already we have calculated the value of DC from, we have selected the value of DC from the standard table. And if we will increase the length of the threaded portion of this coupler nut, then area is going to increase and induced stress or shear stress is going to decrease. Okay, so by using this formula we can calculate the length of coupler nut. So I am going to rewrite this equation in terms of L, because we have the value of tau, we have calculated the value of DC, we have calculated the value of PD, that is design load. So the equation can be L is equals to PD divided by pi DC into tau. So let us put the values of DC, tau and PD in this equation and calculate length, that is length of coupler nut. Okay, so here PD is 78,000. Again we are dealing with the threaded portion. So I have considered I have selected the design load divided by d pi into DC. DC already we have selected DC 36.416, and tau is the permissible shear stress, which is already provided in the numerical. So it is 45. Okay, so let us calculate. So I have found that length is 15.16 mm. Okay, for this calculation actually the length is 15.16 mm, but here the same length we can calculate by using the empirical relation. So in actual practice, the length of coupler nut by using empirical relation, it can be taken as D to 1.25D, where D is the measure diameter, which already we have selected from the table. So let us calculate D. L is equals to D will be 42 mm, because D is 42. We have calculated, I have discussed in the previous slide. We found that D is 42 mm from the table. So we can take the value of D, L is equals to 42 mm as it is, or we can go for the higher one, L is equals to 1.25D, which will be 52.5 mm. So right now for this I am going to select the value, and this is the smaller one as per the calculation by using by considering the shear failure of threads. The length is 15.16 mm, and by considering the empirical relation, it is 42 mm, and this one is 52.5 mm. So I am going to select the middle one. Okay, so L will be equals to, therefore we shall take the length equals to 42 mm. So finally we have calculated the length. So let us do a check for whatever we have calculated. We have calculated the core diameter, we have calculated the nominal diameter, and we have calculated the length. So whatever the selected core diameter, selected measure diameter, and for the selected length, so we should check that whether the design is safe in crushing or not. Okay, so next is we are going to check the induced crushing stress in the threads. Okay, so here once again here you can see the figure. When a force of magnitude P is applied, okay, so these are the selected values, B, C, D and L is equals to 42 mm. For these selected values, I am going to check how much amount of crushing stress will get induced after the application of force of 78,000 Newton. Okay, for the design load of 78,000 Newton. Okay, so here you can see the threads. This is the length of coupler nut. Okay, so after the application of force of magnitude P, here for the single thread I am going to show you along this flank. If suppose the acting force is acting towards the along this direction towards the right side, the force of magnitude P is acting, okay, or PD is acting, the left flank of threads, this is the left flank of every thread, it will be get crushed. Okay, so this will be under crushing stress. If the force is acting towards the left, then the right side will get crushed. Okay, so we need to calculate the area under crushing. Okay, so this area, in this area here you can see that here DC is the core diameter. Already we have calculated from this point to this point. Okay, and this is the measure diameter, that is nominal diameter D. Okay, so here you can see that. So we need to calculate this area of this flank. Okay, so it will be under crushing stress. So it will be A is equals to, here I have mentioned that the crushing stress will be equal, sigma CQ will be equals to PD. Again we are dealing with the threaded portion, so I have selected here the design load PD divided by N. N is nothing but it is number of threads present over the length of the nut, and A is the area of single thread. Okay, so area of single thread will be pi by 4 into D square, that is measure diameter of threaded portion, minus DC square, that is core diameter. Okay, so area of one thread will be pi by 4 D square minus DC square. So let us put this value in this equation of sigma CK. It will be sigma CK is equals to PD divided by pi into bracket D square minus DC square into N, where N is number of threads. Okay, so by using this equation we can calculate the induced crushing stress. Here we have to put the value of D, which is already we have selected from the standard table. It is 42 mm. We have selected the core diameter, it is 36.416. Okay, we have the design load PD, which is 78,000 Newton. But we don't have the value of number of threads. Then how to calculate number of threads? Okay, so here we can use the formula of number of threads. N is equals to length of coupler nut. Here this is the length of coupler nut, threaded portion, length of threaded portion of the coupler nut, which is L. Okay, divided by pitch. It means that pitch is the actually nothing but it is the distance between the two, point on a thread to the adjacent point on the next thread. Okay, so pitch is nothing but this portion is called as pitch. We can consider this as a pitch. Okay, this portion is pitch. Okay, so this the value of pitch is, whether the value of pitch is available. Yes, it is available in the table which is provided in the numerical. So let us check the table. So we have selected the core diameter 36.416, nominal diameter 42 mm. It means that we are going to select the bolt of, for the nominal diameter of 42 mm, for the core diameter of 36.416, we are going to select a bolt of M42 size. Okay, so for this size the pitch is 4.5. Here you can see the pitch. Okay, so select the value of pitch from this equation. We have the length of coupler nut, which is 42 mm. So let us calculate the number of threads. It will be 42 divided by 4.5 is equals to 9.33. Okay, so here the number of threads are 9.33. Put the value of number of threads, put the value of D, DC, PD and N, you will get the induced crushing stress. Okay, so here the induced crushing stress will be, as per the calculation, it is 24.3 Newton per mm square. But in the numerical, they have provided the allowable or permissible crushing stress, it is 90 Newton per mm square. So here you can see that for whatever the dimensions we have selected from the standard table, we have selected core diameter of 36.416 mm, we have selected the nominal diameter of 42 mm, we have selected the length of 42 mm. For this selected lengths, we have calculated the induced crushing stress, which is 24.3. So it is less than 90 Newton per mm square. That means that our design is safe. If the sigma ck it will exceed 90 the allowable or permissible crushing stress, if it will be more than 90 Newton per mm square, then we have to go and redesign the threaded portion. We have to check where is the mistake exactly. Okay, so right now there is no need to check because our design is safe. Our induced crushing stress is less than the permissible or allowable crushing stress. So the design of coupler threaded portion of the coupler nut is safe, okay, and crushing. Next is let us calculate the outside diameter of coupler nut. So here you can see that the outside diameter of coupler nut is D. This is the outside diameter of coupler. So we are going to find out capital D. So here you can see that this is the wall thickness of the coupler. So when a force of magnitude P will be applied on the rod, there is a possibility of failure of coupler nut along this plane and along this plane. Okay, so we need to calculate the area under tension. Okay, so here the tensile failure of coupler nut is possible. Okay, so once again I am going to take the previous values that we have calculated, that is DC, D and L. Okay, so for the design of coupler nut, I am going to consider the tensile failure of coupler nut. Sigma T is equals to P divided by area. Then area under tension, here you can see that the area under tension here, it looks like a hollow pipe which is having internal threads. Okay, so after the application of force, it will fail in a tensile manner. Okay, so the area will be pi by 4 because this is of a circular cross section. The threaded portion of a nut is of a circular cross section. It will be pi by 4 capital D square minus small d square. The small d square is nothing but the nominal diameter of the rod. Okay, so it will be A is equals to pi by 4 capital D square minus small d square. So by using this formula, I am going to put this formula in the equation of sigma T. It will be sigma T is equals to P divided by pi by 4 d square minus d square. Okay, so by using this formula we can calculate the capital D because we have the value of D which is 42 mm, which is selected from the table. Here I am going to remind you that I have considered the normal applied force. Okay, here we are not dealing with the threads, we are dealing with the coupler nut. Okay, so here I have considered the nominal load, I have not considered the design load. So you have to remember that during the exams, only for the threaded portion we have to consider the design load. For the remaining portion of the coupler nut or for the remaining part of the turnbuckle, we have to consider the provided nominal or normal applied force, which is given in the problem. Okay, so here by using this formula we can rewrite this equation in terms of d square. So let us rewrite this. It will be d square minus d square is equals to P divided by pi by 4 into sigma T. So it will be d square, capital D square is equals to 4 P divided by pi into sigma T plus small d square. Okay, so let us calculate capital D, that is the diameter of coupler nut. So let us put the value of P, sigma T and small d. It will be, so by calculation I found that capital D, that is the major diameter of coupler nut, it is 52.75 mm. Okay, so by one more way we can calculate the outer diameter of the coupler nut by using the empirical relation. So in actual practice the diameter of coupler nut D is taken from D to 1.25 D to 1.5 D. Okay, so let us calculate. So here for the dimension of D is equals to 1.25 D, it will be 52.5 mm, and for the equation of D is equals to 1.5 D, it will be 63 mm. Okay, the outer diameter will be 63 mm. So here you can see that the calculated one is 52.75. As per the empirical relation, first one is 52.5 and second one is 63 mm. So I am going to select you can go for the selection of this also by empirical relation, sorry, by calculation. It is 52.75. If we'll round it to the next digit, it will be 53 mm, and if we'll select this d is equals to 1.25 d by empirical relation, again it will be 53 mm. So I am going to select this one. Okay, so I have rounded it to the next digit. So the outer diameter of the coupler nut is 53 mm. So finally we have calculated the outer diameter of coupler nut. Okay, next is the outside diameter of coupler. So here you can see that again the outside diameter is this portion of coupler nut. We have to find out this outside diameter, and there is one more inside diameter is also there, d1. Okay, so here we can see that after the application of tensile force of magnitude p, because here I am going to consider the normal applied force instead of design load. I am going to consider the normal applied force because we are dealing with the coupler, not the threaded portion. Okay, so after the application of force, there is a possibility of failure of this portion in tensile manner. Okay, so let us see. The permissible tensile stress sigma t will be equals to P divided by area under tension. So this is the area of under tension. So if you will consider this is the circular part, actually it is the circular part. Internal diameter is d1 and outer diameter is d2. Then it will be area will be pi by 4 d2 square minus pi by 4 d1 square. Then it will be a is equals to pi by 4 d2. That is the outer diameter of the coupler, which is actually looks like a hollow pipe, which is having the internal diameter d1 and outer diameter d2. Okay, so put the value of a in this equation. It will be sigma t is equals to P divided by pi by 4 d2 square minus d1 square. Okay, so here we can select the value of sigma t, which is the permissible stress and tension, which is provided in the numerical. We have the value of P, which is also the normal load, which is provided in the numerical. We have to calculate the d2. We should have the value of d1. d1 is nothing but it is the internal diameter. Okay, here this is the internal diameter, and we can calculate the internal diameter by using the empirical relation. So here we have the relation d1 is equals to d plus 6. D is the nominal diameter of the rod of the threaded portion that we have already selected from the table. Okay, it is 42. So d1 will be 48 mm. So once you will calculate d1, it will be easy to calculate d2 because remaining values are already given in the problem. Okay, so let us calculate d2. So here I have written this equation in terms of d2 square. It will be d2 square is equals to pi by 4 sigma t plus d1 square. So put the value of sigma t and d1, which already we have calculated. We can calculate d2. So by calculation I found that d2 is 57.64 mm. Okay, once again I am going to calculate d2 by using the empirical relation. So what in the empirical relation, d2 is taken from 1.5 d to 1.7 d, where small d is the diameter of a rod. Okay, or is the nominal diameter of threaded portion. So d2 will be, if you will take the d2 is equals to 1.5 d, it will be 63 mm, and if you will take d2 is equals to 1.7 d, it will be 71.4 mm. So if you will see, this is the value of d2 according to the calculation. Okay, so this is the stress by considering the tensile failure. Okay, so it is according to the permissible tensile stress, d2 will be 57.64. According to the empirical relation, d2 will be 63 mm and d2 will be 71.4. Here from the above these values, I am going to select the outer diameter d2 for the coupler of 63 mm. Okay, next is the length of coupler nut between the nuts. So these are the two nuts between which the length of coupler nut capital L, and that can be calculated by using the empirical relation L is equals to 6d. Okay, so length of coupler nut will be coupler will be taken as 6 times the diameter of nominal diameter of the rod. So it can be it is 252 mm. Okay, so as per the calculation. Next is the thickness. Wall thickness of the coupler is T. It is represented by letter T. It is 0.75 times the diameter. It is 31.5. So I have rounded to the next digit of 32 mm. It is 32 mm. And if you will take a look, if you will see in the side view, the thickness of this is the open type of coupler. In case of open type of coupler, you will see this type of profile in the side view. Okay, so thickness of this wall is represented by T1 and it is 0.5 d. Okay, so it will be 21 mm. Okay, so that's it. We have calculated all the dimensions of turnbuckle. So let us see. We have calculated the core diameter, we have calculated the nominal diameter, which is 42 mm from the table. We have selected it from the table. We have calculated the length of coupler nut, this portion, the threaded portion, which is 42 mm. We have calculated the induced crushing stress, which is 24.3, which is less than the permissible one, so our design is safe. We have calculated the outside diameter D, it is 53 mm. We have calculated the outside diameter of coupler also, D2, it is 63 mm. We have calculated the length of coupler, it is 252 mm. We have calculated the thickness, wall thickness and side wall thickness, it is 32 mm and 21 mm respectively. Okay, so that's it. Thank you. So